a little bit of, oops, got that right. a little bit of science thrown in as well. So thank you so much for inviting me to come and talk this evening. Yes, the title of the talk, T-shirts on for an Arctic Heatwave, is actually a headline from a newspaper, which I'll share with you in a moment. I'd like to just give you an overview of some of the research work we do in the high Arctic, why it's important, and tell you a few stories. And there will be a polar bear picture or two at the end in case anyone's come just for that. More on that towards the end. I can see someone's got their hand up. I didn't know if I should be. No, okay, that's gone down. So yes, I'm a glacier scientist, and I've been working in the high Arctic for almost 30 years now, which is a very privileged career, in my opinion, seeing some of the world's most beautiful locations. Hopefully the picture here gives you some indication of some of the wonderful scenery. But it comes with a bit of a sting in the tail, having seen the very rapid and accelerating changes in the region over that 30-year career. So in terms of why I'm interested in Arctic glaciers and why they matter in general terms, as I'm sure you're probably aware, the Arctic is warming. It's the most rapidly warming part of the planet at present, more than double the global average. Arctic glaciers, particularly small Arctic glaciers, very sensitive indicators of climate change. And when I use the term climate change in this regard, I'm referring not just to temperature changes, but also to precipitation changes in the high Arctic. Rainfall, very effective at melting ice, and we're seeing a wetter Arctic, and snowfall is the, if you like, the nourishment. Glacier ice is nothing more sophisticated than compressed snow. And we're seeing accelerating changes, particularly over the last decade. And I'm actually a glacier hydrologist, so I'm particularly interested in the water side of things, as you'll see shortly. And so I'm interested in the responses of Arctic glaciers to environmental changes, particularly in terms of their water production and associated sediment and nutrient production and movement. I'm not a sea level scientist, as it were, but clearly there is the obvious sea level implications associated with the melt of land-based ice. I also have interests in Himalayan glaciology, and that's why I've just put the water resources bullet point on there. Less of an issue in the Arctic, apart from the communities that rely on snow and ice melt there, more of an issue for the wider world, particularly Asia, with the Himalayas. So here is where I spend most of my summer months when I'm not at the university. The Svalbard archipelago, which is a group of islands in the Barents Sea, very northerly latitude, but a very important location for studying glaciology and glacier hydrology, because, as I mentioned earlier, small glaciers are much more responsive to environmental change than large glaciers. Now, of course, Greenland has plenty of large glaciers and is a center for research. But by contrast, Svalbard has rather more small glaciers which respond much more sensitively. They have much shorter lag times in terms of their response to changing snowfall inputs or indeed changing melt. So Svalbard has become a real center for glaciological high Arctic research. Here is the newspaper report that forms the basis for the title of the presentation. I was in Ny-Ålesund, the world's most northerly permanently inhabited settlement, in summer 2005. And we were indeed dressed in t-shirts. There is a photo somewhere of somebody wearing t-shirts, a t-shirt, shorts and flip-flops. Why do you have flip-flops in the Arctic? That's a good question. It's so we have some footwear in the research base inside, and we're not bringing in dusty shoes and boots. So 19.6 degrees C. in 2005. So that was a record at that point. And the Observer sent up a reporter to report on this. Interestingly enough, just as an aside, Hillary Clinton also paid a visit in the Ålesund with Senator John McCain in 2005. They were on a fact-finding mission with a climate change agenda. And I found it quite interesting that we have to carry rifles for polar bear protection. And so you've got all these armed scientists on the research base, and Hillary Clinton is just wandering about. So it was a rather surreal experience. And then that record was broken in 2020 with a temperature of 21.7 degrees C recorded in Longyearbyen, which is the main settlement in Spitsbergen, which is the largest island in the Svalbard archipelago. So some pretty rapid changes taking place in the high Arctic, which makes life very interesting for we glaciologists. Now, I mentioned earlier I'm a glacier hydrologist. That's my main focus. So I work on land-based ice mostly. And one of the issues with being a glacier hydrologist is trying to understand how glaciers work inside. Because we can measure inputs to glacial systems fairly easily. I'll show you some photos in a moment. We can measure outputs fairly easily. And really the goal of glacier hydrology is to predict how much meltwater is going to emerge from these glaciers and when. It's that prediction which is so important in terms of predicting future sea level rise, for example. Going back to the Himalayan context, it's important to understand or to be able to predict in terms of future water resource availability. But the problem we've got is the glacier is inaccessible relatively, although I'm going to show you some pictures from inside a bit later on. And in the geosciences, we refer to a system where we have no knowledge of the functioning of it as a black box. So we can measure the inputs, we can measure the outputs, but we don't know how the system operates inside. And being able to predict how much water is going to emerge from glaciers and when, we've really got to understand how that black box functions. And that's really the focus of my research and what I'm going to talk to you about this evening. I like to use the analogy of a Swiss cheese. It's maybe not the best analogy, but you can imagine the glacier being full of holes, full of pipes, full of tunnels, full of caverns, cavities, etc., which channel, which store water, and make the link between inputs and outputs very much more complex than you might imagine. And trying to understand that complexity is fundamental to those predictions or our ability to predict. So here we are in Spitsbergen. This is measuring the input side. So standard meteorological variables to try and assess energy inputs to the ice surface. And to measure melt rates. That's all relatively easy. We can also measure snow accumulation relatively easily. That's no problem. Here is the output side. The majority of output is in the form of channelized meltwater, and that again is relatively easy to measure. But what is much more difficult is linking those inputs to the outputs, and that's where the challenges start. So let's take you on the journey then to Svalbard. This is a picture of Longyearbyen, the main settlement, and I put this picture up for two reasons really. One, it's a fairly pretty picture. I hope it comes across well on your screens. Nice soft Arctic late summer light, but also to just show that the high Arctic is perhaps not the pristine white wilderness that we might imagine it is. A huge amount of human activity going on across the Arctic, and this is something we teach our students in geopolitics lectures, for example. There's huge strategic importance in this region. But also a lot of industrial heritage, and a lot more development and economic activity than you might imagine. So you've got the port here, the main port of Longyearbyen in the middle distance. You can just make out the airport buildings in the far distance, houses and pipelines, etc., also in view there. And much of the work I do is in a place called Ny-Ålesund, which is in northwest Spitsbergen. It is the world's most northerly permanently inhabited settlement, and it's famous for that. On the way to Ny-Ålesund, we do indeed get some nice views of that kind of coffee table book idyll of the high Arctic being a wonderfully beautiful, white, pristine wilderness, which of course it is in large parts, but as I say, not as much as you might imagine. So some wonderful views. We take a small turboprop aeroplane further north, or a boat. It largely depends on the season and what we're transporting. And here is Ny-Ålesund, the world's most northerly permanently inhabited settlement. I've put this photo in just to show you the extent of the settlement. It owes its very existence to coal mining, which used to be undertaken here from the early 20th century. It's now become a research community. So the buildings you can see are all research stations from a variety of different nations. And there are occasional tourist boats docking in Ny-Ålesund, small tourist boats. I'm not talking about large cruise liners, obviously, where suddenly the population of the town goes up about tenfold, which is quite bizarre if you're working there, suddenly people wandering around. But I also put this photo in to show you some of the changes we're seeing in the high Arctic. This photo was taken in early March, so the polar night has only just ended. Sun's come up, and as you can see, relatively little snow. We are seeing a drier Arctic in winter and a wetter Arctic in summer. And you can see the fjord on the left-hand side of this image, completely devoid of sea ice. And that's a situation which has now been the case for probably the last 10 to 15 years since decent sea ice coverage was observed in this part of the high Arctic. Now, famous for being the world's most northerly permanently inhabited settlement, and Amundsen has pride of place in the square, as it were, the town square, or the settlement square. Amundsen famously stopped off in Ny-Ålesund with his airship on his way over the North Pole. So he takes pride of place. And there in this photo is the mooring mast, which his airship, the Norge, was tethered to as he paused in Ny-Ålesund on the way north. So an amazing amount of cultural heritage, as well as the industrial heritage in Ny-Ålesund. And again, it's always quite surprising to see so much human activity and development this far north. So this shot's taken in summer. This is actually taken at 2 o'clock in the morning. We have 24 hours daylight, of course, midnight sun. So here you have the world's most northerly post office, of course. This gets rather boring after a while. We have the world's most northerly everything in Ny-Ålesund. Believe it or not, there's a pool table in one of the research bases. So guess what? That's the world's most northerly pool table. And so it goes on. And the post office doesn't really serve much function these days. It did in the coal mining days. But if you are on a cruise ship and you stop in Ny-Ålesund, you can jump off and get your postcards stamped at the world's most northerly post office. Here's the world's most northerly train. This is a relic from the coal mining days. This train is wonderful to see, actually. It's a real sort of feature of Ny-Ålesund. Doesn't run anywhere anymore, of course, but it is preserved. It used to take coal from the mines to the port, and I can only imagine the conditions the coal miners endured mining coal this far north with the extremely harsh environment. But it does make for some very nice photographs, and it's obviously a main tourist attraction on the rare occasions when tourist ships dock. We also have to take polar bear protection very seriously. You're not allowed out without a rifle, and we have to undertake rifle training before we're allowed to carry a gun, and it's mandatory to carry a gun outside the settlement. And so before we head out, we have to prove that we can shoot 4 consecutive shots into an 18-inch diameter target from 50 meters. Now that's really, really difficult when you're completely calm and relaxed and, everything's in your favor. So goodness only knows what it would be like if a large white hairy mammal was thundering towards you. Thankfully, I've never had to fire in anger, but as I say, it is mandatory for obvious reasons. Evidence of science everywhere you go in the Ollison. So this is some way from the main settlement. These domes which seem to pepper the landscape, and where you have scientists, you have science humor. This is one that made me chuckle last time I was up there. Big scary laser, do not look into beam with remaining eye. So scientists everywhere and their humor. Now, here's a bit of a story then in terms of what it's like to work in the high Arctic and some of the challenges we face. Now, if you've ever watched a documentary about airline accidents, one of the things you often hear is that airline accidents don't happen because of one cause. It's a whole sequence of events which ultimately lead up to the accident. And if any one of those events doesn't happen, then the accident wouldn't have happened. And it's a bit like that with research in the high Arctic. There is a mass of logistical challenges to overcome. And this particular project, where we were drilling to the base of a glacier, drilling through about 360 meters of ice, I was the last link in the chain. So I was the last person upon whom everyone was relying, because I was the alleged expert in field instrumentation and installing these instruments at the bottom of a deep borehole. So all the pressure was on my shoulders, but I felt naively reassured knowing that this whole series of highly improbable circumstances had to come about for me to end up in the firing line, as it were, with the last piece of the jigsaw. So I hope you can see this on your screens. I don't know if any of you work in higher education, but the first thing we have to do is actually get grant funding to allow us to do the research. So I'll read through these in case they're not visible. The font is a bit small. And I was fairly relaxed because although all the pressure was on me at the end, it was fairly unlikely that everything was going to go perfectly well. And that's fine. There was plenty of excellent research going on before the final piece of the jigsaw where I came into it. So we apply for the grants, which is, those of you who may have experienced higher education know is a fraught with difficulty. Chances of success are relatively limited. We then get the grant, which was remarkable. We then got to arrange time off work during term time to get 6 people up to the high Arctic. Now, that's not as easy as it sounds, given that we're 6 people coming from 4 different countries. We then have to hope for good weather, because the flights, internal flights in Svalbard, only operate under visual flight rules. So low cloud is a no-no. And Spitsbergen is renowned for being foggy. We then have to get about 6 tons of equipment shipped up to Spitsbergen, again, reliant on those flights operating. We've also got to get that equipment there in one piece. Easier said than done. I'll explain one particular issue we had in a moment. Some of that equipment has to be helicoptered onto the ice. which is very, very weather dependent and very difficult, fraught with problems. Then we drill to the bottom of the glacier, which itself is a massive logistical enterprise and usually doesn't end in success, because what usually happens is you get to 200, 250 meters or some tantalizingly close distance to the base of the glacier, and you hit a great big rock. And because the drill operates not on rotary motion, but on hot water, it melts its way to the base of the glacier, it is hugely frustrating. And so if the planets align, if all these individual components work, if they all come together, then eventually you reach the glacier bed. And of course, that's then when I'm left feeling rather nervous, because I'm the last person in the chain, and it's now up to me to perform and get these instruments installed and get everything working properly. So guess what? First time, everything happened. Everyone got time off. Everyone got their flights okay. The weather was wonderful. The equipment got there in one piece, apart from one of the drills, which one of our technicians at another university had filled with water rather than antifreeze. I'm sure you can imagine what that did to the drill when it reached Nyhavn at -20. The helicopter flew. We got most of the equipment up first go, and believe it or not, the first borehole we drilled got straight to the bed first go. So one in probably tens of thousands chance of that actually happening. So hence my rather now anxious state of mind, not helped by this lot, which is probably about a tenth of the equipment that I had to wire and solder and program and hook up to the data logging equipment, because this all has to go into the ice. So here is our prime helicopter flying day, a very rare clear blue sky day in Spitsbergen. We're getting ready to helicopter our equipment onto the ice. Here's a view from the cockpit, and I hope this video works, but I'm just going to show you a video of us taking off, heading up onto the ice. And what you can see down here in the middle is a stopwatch, and this adds to one's anxiety when doing research, because the stopwatch is started as soon as the pilot turns the key in the ignition, as it were, and it doesn't stop again until the rotor stops spinning. And the cost of helicopter hire in Svalbard is astronomical, and so as that clock ticks away, you watch your grant funds drain out of the bank account before your very eyes, and of course you're then left hoping and praying that the helicopter is actually able to reach its destination, drop the equipment okay, without having to do a second flight, which gets very expensive. So and helicopter work in the Arctic is very, very difficult. I take my hat off to the pilots. The light conditions have to be pretty much perfect. We're in a very low contrast environment, and often the pilot will get halfway to the glacier and then just turn back. Can't get enough visual differentiation between the ice surface and where the equipment needs to be dropped. And so they turn back. So it can be very, very frustrating. Here's a view looking up to the helicopter. This is a pulse quickening activity, a helicopter buzzing above you with a 600 kilogram load slung underneath it, and you have to maneuver it down into position. I don't know if anyone's worked around helicopters, but I find it extraordinarily stressful. The noise, the winds, the snow being whipped up, as you can see here. And of course, this frequently happens. You can see here the low contrast light now. The clouds come in and we're left waiting for the helicopter to come back. So there is an awful lot of this going on. We get ourselves up there most of the time on snow scooters, and often we'll get up there, the helicopter will come up, it will make one drop, it will then go back to base, and we're then left up on the ice for 8, 12, even longer hours until we get the call that they're calling it off for the day. So it becomes rather stressful, and we have to wrap up warm. So it's just a shot of me waiting for the helicopter, trying to keep as warm as possible. About minus 15 to minus 20 usually up at this altitude where we're drilling through the glacier. And this is drilling day. I use the term drilling, but we're actually melting our way to the glacier bed. So we can put instruments down to try and explore that black box, understand how the glacier moves and how water interacts with that movement, how water is stored, how it's transmitted. These are pressure washers, industrial pressure washers that heat water, pressurize it, and then pump it out at just below boiling point. We have 2 of them going continuously. We have an automated hose reel, which you can see on the right-hand side here. The high pressure hose goes over the tripod in the background and essentially just melts its way to the base of the glacier. And here's a picture of the drill rig set up. We take it in turns to operate the drills. They need regular attention, refueling, etc. Very important, somebody is always alert for the polar bear risk. And these are very, very long days indeed. And I'll show you, demonstrate just how how morale sapping the long days can be in a moment. But this is a photo of the actual drill hole itself. You can see the high pressure hose in the middle, just lowering its way through the ice. The green hose is retrieving meltwater from the borehole, because liquid water at this time of year is a very precious commodity and we want to reuse it. So we have a pump drawing water out as we melt it, recirculating it and feeding it back into the drills to be reheated. Now, I hope this is, I hope you can still hear me above this, but here is the drill itself, the automated reel. My colleague here is scratching his chin. What he's actually doing is he's working out the drilling rate and trying to work out what time we're going to get to bed. Now that's the discussion taking place. So let's leave them to it. Here is our tank where we recirculate, we store the recirculated water ready to be drawn into the drills again. And now if you look at my colleague's face again, he's just made the calculation and worked out what time we're going to bed. And as you can see, he doesn't look too pleased about it. This was a 22-hour work day. So we started at 8 o'clock in the morning and we finally arrived back at base at 6 o'clock the following morning. So it was a very, very grueling day. But here's journey's end, if you like. This was our miraculously successful hole. First go, straight to the bed, 360 meters deep. And although I'm smiling, I'm now very, very nervous indeed, because I am the last link in that chain of events, that improbable chain of events that I showed you earlier. And so everyone sits back and lets me do the last bit. So no pressure then. Which is to install the instruments in the borehole, wire them up to the data logger, program the data loggers, check everything is working, etc., etc. Which thankfully I was able to do. And here is our setup, which we leave over winter. The case on the left houses batteries. We've got solar panels, trickle charging those batteries during the Arctic summer. And those batteries have enough power to last the Arctic winter. The small Pelly case you can see at the top of the photo is a remote telemetry system whereby we send a radio signal to a repeater station on a high pass, which then sends a signal to the mobile phone network down in Longyearbyen. So we are able to remotely check data. Now, one of the main things we're looking at with this ice drilling experiment is looking at how water pressure at the base of the glacier changes, because we drill the borehole, we can insert a pressure sensor in it, which is what's being shown on the left there, not to scale. And as the water pressure at the base of the glacier fluctuates, we pick that up as a rising and falling of the water level in the borehole we've drilled. We use a data logger, which I've just got a picture of at the top, and we can monitor that signal as that water pressure fluctuates. It has profound impacts on glacier motion, and particularly as we see potentially more water getting to the base of glaciers in the high Arctic, we are seeing some speed up events, which is really fascinating in terms of how these systems are responding to the environmental changes that we're seeing. Now that's extreme remote sensing. We're drilling a hole through 360 meters of ice. The hole is about 3 inches wide at the base of the glacier. And that's one tiny part of that black box that we're so interested in to understand how the hydrological system works. We can use this technique, which is called fluorescent dye tracing, to supplement that borehole work. And what I'm doing here is pouring a fluorescent dye into a surface stream on the ice surface. That dye then flows into the interior of the glacier via a large hole called a moulin, which I'll show you a picture of in a moment. I should add that this looks like environmental vandalism. It's not. This is a perfectly benign dye we use, which photodegrades very rapidly and doesn't leave any long-term residue in the environment. But if I just show you this conceptual animation, this is a gross simplification, but one of the things we can tell is if we lift the glacier off the surface and we look at how the dye flows, in this diagram you can see the channels at the base of the glacier are relatively straight, and they move water quite efficiently. They don't store water very well. And so that's important in terms of how the glacier is responding and how much water will emerge and when. We can anchor the fluorometer, which is the device at the bottom of the photo, the slide here, at the meltwater stream in front of the glacier and look at the sort of signal that it picks up. And where we get this sort of relatively simple signal, quick rise and fall to peak, we can deduce that the hydrological system is fairly efficient. It's not storing water particularly well, but it is transmitting water through the system quite quickly. And we can build that into predictive models. Conversely, here is a rather more complex drainage system, multiple pathways for water, delaying the flow of water to the front of the glacier. As you can see, we get a much more complex response from our fluorometer. Now, I've kept the scale the same just for clarity, but the fluorescence we measure in the meltwater stream is going to be a much more complex, a more diluted response, and it's going to be drawn out over a much longer time period. So we can learn a good deal through this relatively simple technique, supplemented by our borehole work. But really, to really get to the bottom of how glaciers look, how they function inside, how they channel meltwater, we've got to get inside. And we have a wonderful opportunity to do just that in the high Arctic in the winter, or late winter, early spring. You can see we have some light here in this picture. I hope you can see just on the far right, there is a stake marking a very large hole. And I put this picture in deliberately because you can't see the hole. The lack of contrast with the light is quite incredible. This is one reason why glacier walking above the snow line is so very dangerous, because you often can't see features until you're right on top of them. So here is a big hole. This is a moulin, a vertical shaft down which meltwater will flow during the summer months. Here's my colleague setting up one of numerous anchors that we have set up ready to abseil into the moulin and map it. Get a detailed map of that internal hydrological system, that black box. So, as I say, numerous anchors. You can't see it in this photo, but we also back up the anchors by tying the rope around a snow scooter, which is very heavy and is unlikely to move. And you have to pity the poor person, my colleague here on the surface, who has to stay on the surface while we're down the hole, just checking no curious polar bears are wandering in the vicinity. That's a really unpleasant job in the wind, in the cold. So here we go. This is me abseiling into a moulin. It's dry, as you can see, because we're in winter-spring transition, no meltwater here. I don't mind telling you, it's the most terrifying thing I've ever done. If this was a video, you'll be able to see my legs shaking. Here's me putting a brave face on it, halfway down. And that's me looking up from halfway down, trying not to look at this large overhanging block of ice above my head. But what we're doing here is using a terrestrial laser scanner to give us a three-dimensional scan of the glacier interior. So not only do we have an understanding of its shape, which is important from a hydrological point of view, but we can see how it evolves from year to year. And here we are calibrating the laser scanner at sea level in Nyhavn. Note the lack of sea ice, and this was a particularly warm day, as you can probably tell from the clothes my colleague is wearing and the lack of gloves. But here we are scanning in the interior of the glacier. This is at the bottom of the moulin. The moulin then leads into channels which flow water beneath within the glacier. An amazing environment. I jokingly say that more people have walked on the surface of the moon than have been this deep into the insides of a glacier. I'm not sure that's true, but it certainly can't be far off. And one of those rare environments where you do, once you're in far enough, see complete darkness. The only other place I've been is the Peak District in the caverns there. If you go on a tour, and the guide at some point usually switches the lights off and you see complete blackness. But so we're illuminating things with head torches here. Just incredibly beautiful environment, albeit rather terrifying for somebody like me who doesn't like confined spaces or heights. But there we go. And much more complexity to the black box, to the internal drainage system than we had anticipated. It was a real revelation. Here is a photograph actually close to the front of the glacier. So we went in via the moulin and along the channels at the base of the glacier until we got to a blockage. And then we came up from the other end. So what you're seeing here is daylight penetrating through to the front of the glacier. And here is another beautiful photo just at the front of the glacier as well. Now you can probably just make out in the center here some rectangular objects. These are checkerboard targets. Here's a better view for you. The laser scanner generates millions of points. It generates a point cloud, and we can only scan a short section of the hydrological system at a time. And so we need a visual reference in between every scan to allow us to stitch together the various scenes. And colleagues from Aberystwyth were in charge of that hugely complex operation. And here is a three-dimensional fly-through of one of our scans. So there's the ice surface. You can see the 60-meter moulin, that vertical section. The colors, I should add, are just for clarity. But here we're back on the surface, and now we'll dive down the moulin. You'll see the climbing ropes that we use to abseil in a moment. So you can just see three lines coming into view now. You can see some rucksacks at the base of the moulin. And now we're off into this channel at the base of the glacier. Much more sinuous than we imagined, much larger channel in terms of the ceiling height. An incredible experience to be able to visit such an inaccessible environment. You can see some of those checkerboard targets being picked up by the scanner there. as we move through this subglacial channel. And there you can see that real sinuosity as we pop back out to the surface. So that's an ongoing project that colleagues at Aberystwyth are leading on. But in case you're interested, I know this is being recorded. Very happy to share the slides with you as well. But there is a wonderful website that our industrial partner has put up, Derry Jones Associates. The URL is there, where you can have a walk through the glacier. So you can head down the moorland, you can look up, you can look round, various scenes grabbed from the laser scanner. So if this is of interest to you, I really encourage you to go and have a look at that. It is in black and white, but it is quite amazing being able to look at it in 3 dimensions. I believe, I don't own the technology, but I believe if you have a 3D headset, a Google Cardboard type thing, that also works on this 3D website. So do have a look at that. And I just wanted to finish with a couple of polar bear pictures, because I could never do a talk about the high Arctic without showing a few polar bears. As I said at the beginning, I've worked in the region for almost 30 years. I've only ever seen 2 bears in all that time. I was beginning to think they were mythical creatures, but here is the most recent bear. This was taken last summer in August. You can see it's a fairly dusty, dirty bear. This is taken with a camera through a telescope, hence you can't really see it's much as a bear. It just looks like a grey blob, but this bear caused us enormous problems, because every time we went out to go and do field work, it would start swimming towards us and or walking towards us, so we then have to come back in. So this delayed us quite badly. And here is a much closer shot of a much cleaner, whiter bear. This was from about 6 years ago. This was in summer. This was a bear who came into our camp rather too close for comfort. We had to scare him away. He then went to this hut you can see in the background, which is a Russian hut, broke the door down, ignored all their food except the couscous, would you believe? So I have no idea why the bear went for couscous rather than the meat and other goodies that were on offer. But there we go. He was a very well-fed male bear, so not a danger. Obviously, the dangerous bears are the mothers with cubs, or bears that are hungry or unwell. So I hope that's given you an interesting overview of some of the research we do in the Arctic, and showing you some of the environments we work in. And I have gone slightly over time, because I did promise 30 minutes, but I hope you'll forgive me. And I'll end there and happily throw open to any questions anyone's got.
Thanks very much, Philip. We'll put it back now onto gallery.
I will stop sharing.
I can't hear you, Gordon. You're muted, Gordon.
Sorry, I am muted. I'm not muted anymore.
Oh, good.
So thanks, Philip. It's quite some of the work you're doing is quite scary, but by the sound of it, quite enjoyable as well. So we'll now open up to questions.
I have one there.
Peter.
Yes, my question is, presumably these channels in the ice are caused by water flow. So are you in danger, like you would be in a cave in the Peak District, say, of sudden water rushing in?
Only if you were to do it in the summer. So during the time of year we go, everything is locked up. It's completely frozen, and there's no water in the inside of the glacier. So we're safe in that regard. The one thing that did terrify me is the the drop, although my colleagues obviously reassured me that that was all completely safe, but I didn't feel at all safe. But it was going into the actual channel itself. The Moulin, despite that huge overhanging block, it is relatively safe. It is winter. We're at -15, -20. Ice is very coherent, but what I wasn't comfortable with was in the channel, because you can see evidence of roof collapse, so solid ice collapsing onto the channel floor. And of course, if that was to happen when you were down there and it was a big collapse, as you might also have in a normal cave system, that would leave you in a very difficult situation indeed. So yes, no danger from water, but other dangers. As I said right at the beginning, I'm very privileged to work in these environments, but I don't mind admitting to you here that although it was a bit of a career highlight to be inside a glacier, inside those meltwater channels. I was very happy to get out and back to relative terra firma.
Thank you.
Okay, Peter Latham's got a question.
Yes, I think I've unmuted.
Yes.
There are one or two questions surrounding these cavities or moulins or whatever they're called. I mean, I don't understand whether they're 1%, 0.1%, or 10% of the total volume of the ice. That's point one. And the second point is what is the need to understand the detail of these things and how they flow. I don't quite understand why.
Okay, yeah,
we know water flows through.
Yeah,
and it presumably starts out where it starts and ends towards the face of the glacier eventually.
Yeah. No, that's a very good question. And I could do a whole talk on subglacial hydrology and its importance, but I don't think that would be of interest to the majority. But yeah, the moulins are really interesting features. They are, as I say, vertical shafts which drain water into the hydrological system. They're usually formed either through thermal erosion, so the heat generated by flowing water, but more commonly where ice is fractured through tension, so crevasses and cracking, and then the water exploits that. In terms of the percentage of the glacier that is occupied by moulins, very, very small. That particular glacier we work on has about 5 moulins, which are the main entry points for water to the hydrological system. The moulins themselves are actually not the main point of interest. It's the subglacial channels through which the water moves, because that has a direct impact on glacier motion and how quickly glaciers move. Because where we get water that's pressurized at the base of the glacier, that facilitates fast motion. And so that has impacts on discharge of ice, for example. But also the rate at which water moves through the system and the extent to which water is stored in that subglacial system will dictate the timing of water exiting the system. So if we're trying to predict, as I mentioned right at the start, how much meltwater will emerge from the glacier and when, we've really got to understand the morphology and the functioning of these subglacial channels, these subglacial reservoirs, the extent to which subglacial waters are heading into groundwater, and so that represents a loss from the system. Does that
answer your question, Peter?
Help answer? Yeah, I do a whole series of lectures on glacier hydrology as part of one of our final year courses. It's a huge topic area. So yes, I hope that I'm being very sort of brief, I suppose, but I hope that gives some insight.
Okay, a question from Ian Priest.
Yes, I thought that was absolutely riveting talk.
Thank you.
And very well presented. 2 questions really. One is that if as much as a common understanding, the glacier is on the move all the time. How are the instruments that you put down the hole that is so difficult in terms of project management to get down? How are those protected against movement? And the other some ways related question is, how fast is the glacier receding?
Yeah, good question. The instruments have to be really robust, obviously, really robust. The pressure sensors, which is one of the instruments I was talking about, are cast in a resin, and the pressure sensor itself is metal. It has a metal diaphragm which flexes in response to water pressure fluctuations, but the whole thing is housed in resin. And then the cables you saw in one of the photos of the big mess in the office in the research base, they're extraordinarily strong. And for instruments which are liable to move, because that pressure sensor will remain static in the ice, we use, believe it or not, a stretchy cable, which is it's bizarre to see, but it's an electrical conductor which you can actually stretch. It has flex in it, and so it's able to accommodate the movement of the glacier. So that works quite well. I'm pleased to say the instruments I showed you in the presentation were installed in 2019, and they're still operating today. So we obviously did something right, which was a big relief to me. In terms of how quickly the glacier is receding and how quickly the glacier is moving, well, how fast glaciers move is kind of a how long's a piece of string question, because it very much depends. So I could point you towards glaciers in Greenland that are moving at kilometers per year speed, and glaciers in the high Arctic that are moving at a few centimeters per year. And the same with recession. Recession varies widely. Looking at the way a glacier front moves is not a particularly reliable indicator in terms of impact of climate variables, because what we see in the high Arctic is glaciers frozen to their bed. So they're frozen solid to the substrate, and they're not very dynamic at all. And so rates of recession vary widely. Tidewater glaciers, which are glaciers that terminate in water, are the ones which really are retreating the quickest at the moment, because you've got, if you like, a double whammy. You've got the very fact that they are buoyed up by water, and so you've got tidal flexure, which tends to facilitate rapid movement, but you've also got thermal erosion of warm ocean waters as well. So there is a wide variety of recession rates. I can point you towards a fantastic website, the World Glacier Monitoring Service, which gives annual updates to glacier movement or glacier frontal position, but also, more importantly, glacier mass balance, which is the entire volume of snow and ice in the glacial system, which is the most useful indicator as to the state of the world's cryosphere. It's a fascinating website. Really commend it to you. It's wonderful. Glaciers from across the world that have been regularly monitored.
Okay, thanks. Jim Tatchell.
Very much.
Thank you, Gordon, and hello, Philip. Just wondering, apart from the very occasional polar bears, what other wildlife do you come across in those parts?
Yes, a very occasional polar bear. I'm delighted to have seen one, because I started working in the Arctic in 1993, and I saw my first one in 2017, and then last year. The most common wildlife we see are seabirds, which is wonderful. Really wonderful, particularly fulmars and puffins. Fulmars are wonderfully friendly birds. When you're out on the boats, they'll just swoop alongside the boat. Really lovely. We do see a lot of seals, which is always a treat, and very occasionally walrus. I've only ever seen walrus once. I did hear an amusing tale about a walrus, though, which was we use rigid inflatable boats in the Arctic for getting around on water, and of course you have the inflatable tube. And this dreadful story of a walrus obviously has big tusks, and this walrus decided to attack the boat and got its tusks locked over the edge of the inflatable part of the boat. So they seem, I mean, a walrus is huge. It's a terrible time trying to get this enormous beast off the boat. But yes, and Arctic foxes are fairly common. You need to be quite wary of them because they do carry rabies. So and Arctic hares as well are reasonably common to see. So yeah, that's kind of I guess probably the most common forms of life we see. We do see occasional whales, particularly beluga, but that's more rare. Not quite as rare as the polar bears, but whenever you see that wildlife, you know, to me, it's just, you know, exemplifies that great privilege of being able to work in such a wonderful region. You know, people pay thousands to go on bird watching holidays to Svalbard, and you know, we've got it all around us every day. It's quite wonderful.
Thanks, Philip. You've been traveling up there for almost 30 years, I think you've said.
Yeah, 1993. So what's that? Yeah, so 29 years. 29. Yeah.
So you did mention that sea ice is now less common.
Yes.
Are there other signals you've seen on global warming?
Yes, I mean, sea ice is the most obvious one. The shot I showed you from the Ollesund is really interesting because when I first went there, it was really easy to get to the other side of the field because you could just get a snow scooter and, you know, zip across the sea ice. And now you've got to go the long way round. But yeah, they're very, very obvious changes to the glaciers. It's really interesting for many of the land-based glaciers where it's not retreat that we're seeing so much. It is vertical downwasting. That's been quite interesting to see. A glacier we work on in near the Ollesund called Ostrobroggerain. We now have a small mountain. Well, calling it a mountain is too strong, but a very large rock outcrop, which offers a lovely vista across the whole glacier if you climb up onto it. But when you're up on it, you suddenly realize, well, hang on, when I first came here almost 30 years ago, this was covered in ice where I'm standing. So now that particular glacier hasn't retreated much. It is frozen to its bed in the lower reaches, but it has vertically melted. The other thing we're seeing signs of, and this particularly afflicts Longyearbyen, where we have habitation, is the thawing of permafrost on the valley side slopes, and the collapse of debris, so mass movement, landsliding, as that frozen ground slowly but surely thaws. So that's been very noticeable. We now have, for example, avalanche fences in Longyearbyen, which didn't exist until very, very recently, and protection against landslides, which again is something that's very new. I did a particularly grisly piece for the BBC a few years ago. I had a brief secondment to the BBC and the radio science unit, which was wonderful, but I interviewed some Dutch scientists who were studying how the graves of whalers from the early 20th century were now starting to emerge from the permanently frozen ground, the permafrost, as things warm up. And that was particularly grisly, but that was something they were researching. There is a cemetery in Longyearbyen, which is on one of the valley side slopes, and there is talk of also having to move that cemetery because that permanently frozen ground is now becoming increasingly thawed, and there is the same risk of graves becoming exposed. So, but yeah, I think the sea ice is the most profound or the most obvious change, followed by this vertical lowering of ice surfaces. Very noticeable in some of the areas we've worked at. And
is there any hope of that trend reversing?
I don't think so in the foreseeable future, no. But it does fluctuate from year to year. That record-breaking temperature of 21.7 degrees C was followed by a relatively good snow year, so that restored a bit of mass to some of the glaciers. But I think one of the things, again, which I've noticed anecdotally, but also backed up by measurements, is how the Arctic is becoming wetter. As it warms, it becomes wetter, and of course that means more rainfall earlier in the spring. And as I'm sure you're all aware, water is very, very effective at melting ice. So it's certainly, it's worrying on one level, and being honest, I don't think there's much chance of that trend of being reversed. But it is also scientifically fascinating at the same time. Yes.
Okay, Peter Latham's got another question, and then Peter Blaskus as well.
Philip, you've just talked about the ice melting. Do we have any reliable historical records so that we can do comparisons with how temperatures and climate might have fluctuated over the years? I mean, for instance, we've been in a long-term cooling phase of the Earth for about 12,000 years or more. And then it goes in 50,000 year cycles or 100,000 year cycles.
Yeah, I mean, you've got the Milankovitch cycle, which is obviously changes in the Earth's orbit around the sun and changes in tilt of the Earth. I mean, we've Antarctic ice cores, we can go back about 850,000 years now with good reliability, proxy measurements of temperature, relatively high resolution. Ocean cores, we can go back even further, but that's much lower resolution record. So yes, I mean, we've had regular swings, particularly over the last 2 to 3 million years, glacial, interglacial, glacial, interglacial, plenty of geomorphological evidence in Svalbard for that all around you. But I think what's remarkable at the moment certainly is the pace of change and the very rapid acceleration of that change, particularly over the last 10 to 15 years or so. That's been really, really noticeable. So a lot of this is being driven by, I mentioned at the beginning of the presentation, the fact that the Arctic is warming more than double the global average. A lot of this is being driven by the diminishment of sea ice. And of course, sea ice is relatively reflective compared to the ocean surface, which is obviously a darker surface, has a lower reflectivity. And so we have a situation whereby the more you expose those darker surfaces, the more energy can be absorbed rather than reflected. So I think from my point of view, I don't view myself as a climate scientist per se, but certainly the pace of change compared to historical records is pretty staggering.
Okay, thank you. Peter Blaskus?
It's just a very quick question, I think. You went down about 1,000 feet or something, was it 350 meters? To
360 meters, about 1,000 feet.
Yeah. 1,000 feet. How many years of snow does that represent?
Oh, now that's a good question. Well, yes, that is a very good question. In Antarctica, 3 kilometers deep will get you 850,000 years. Now that's in the center of Antarctica, where flow lines are not a problem because ice deforms obviously as it flows. That particular glacier, the honest answer is I don't know, but we would be, I would imagine, a few thousand years of history down there. We often joke when we're sometimes on the way back on the boat in the summer, we might pick up a chunk of ice from the fjords, and you can't help but wonder when that ice fell as snow. Was it Roman times? Was it prehistorical times? And that's a pretty, mind-blowing thing to think. That ice could potentially be many thousands of years old. The only way to definitively answer your question, though, would be to extract a core from the upper reaches of the glacier. Now, coring is not obviously what we do, and to count the annual accumulation layers in the ice, much like you would count tree rings, annual growth rings. We can do that from the surface downwards, and you could then come up with the answer to that question. But yeah, I can't give you a definitive answer, I'm afraid, for that particular glacier.
Okay, thank you. Is there one last question? Peter Barber. You're muted.
James has got his hand up.
Yeah, okay, sorry, Philip.
Sorry.
Thank you for such an interesting talk.
Thank you.
Where does your research actually all go to? And is it amalgamated with a whole load of other similar research?
Yeah, it is very much so. I mean, ultimately, this feeds into a larger body of glacier hydrological work. And although I do a lot of work in the Arctic, I also do a lot of work in the Himalayas. And the work we do in the Himalayas builds on the work we're doing in the Arctic and our understanding of how glaciers work internally. So in terms of practical applications, we have constructed predictive models for example, water authorities in Pakistan, in the Hunza Valley, whereby they are using glacial meltwater for hydroelectric power generation, and they want a reasonably accurate means of predicting exactly what I mentioned at the beginning of the presentation, which is how much water is going to emerge from a given glacier and when. And so it's using that knowledge of how the hydrological system functions in conjunction with surface measurements, which the authorities are able to gain from satellite images. This is a whole nother lecture I could do for you, actually, which I'm very happy to come back and do on Himalayan exploration and field work. And they can get their daily predictions of meltwater production and manage their hydroelectric facilities as a result. So obviously, some of what I do is purely academic. Some of it informs sea level rise work that is passed on to other colleagues. Some of it informs our greater understanding of how that black box functions, which we can then build into the more applied nature of that research in terms of the water resource management issues in countries like Pakistan, India, Nepal, Tibet, etc. And that is really where, for me anyway, a real sort of pleasure in research comes, actually seeing that research being used for practical benefits and practical application.
Okay, thanks.
Thank you very much, Philip.
Thank you.
James?
Just a very quick one. Firstly, thanks ever so much, Philip. I mean, that was incredible. I mean,
Thank you.
Sure. I mean, the preciseness and the various, but I wonder, Peter Blaskos mentioned thousands or meters going down. When you as a human are going down there, how do you get your oxygen to breathe when you're so low?
Oh, well, the borehole is drilled 1,000 feet. So we're not down at 1,000 feet. So there's no issue there. And when we're abseiling in, we're probably about 80, 90 meters down. And there is plenty of good airflow. So, and it's actually a bit warmer than it is on the surface, which is quite nice, which is why I pointed out the poor person on the surface who has to sit there with a rifle ready for a polar bear should one come and wander along. So yeah, we're okay for oxygen, for airflow. And it is actually, although as I mentioned, I was terrified when I was in there, and that's not an exaggeration. it was nice to be out of the wind and the cold.
Thanks very much, Philip. That's a wonderful talk, and you've introduced us to a world that probably none of us were aware existed.
Thank you.
And we look forward to our second date with you when we're going to be looking at the Himalayas, I believe.
Very happy to come and talk to you about Himalayan work. That would be wonderful.
And I've got to say, the University of Hertfordshire have provided us with some fantastic speakers over the years. So thank you to them as well. Right, so our March talk, our next talk, will follow a similar theme. It will be about the environment, but delivered by school children. And perhaps we may well meet the next Greta Thunberg. Now, the speakers so far lined up, firstly is Sophie, age 10, from class 6 at Lambert School, who's my granddaughter. And then Zoe and Yvette from year 12, which I think is 16, 17 age, from Hockerell School in Bishop Stortford. I've also been promised two speakers from Tainroyal Academy, which is the school where I attended. It must be 10 years ago now since I was at school, I think. So, and then the following month, in April, will be another talk related to environment when Will Gemmell, the senior partner at Ceres Rural, will be talking about farming. So that all should be an interesting theme that we've managed to collect together. So thanks all for joining us. Thanks for listening. Thanks for some wonderful questions as usual. And could I invite you all to raise your glasses and toast the Queen and Rotary. The Queen and Rotary. So thank you all and good night.
Thank you. Nice to meet you all.
Thank you. Thank you very much.
Thanks.